This is an introduction to proton NMR spectroscopy. Most of what I'm talking about will be under this link, which is in your PowerPoint slides, under the MSU link under proton NMR spectroscopy. Alright, so the whole principle here is based on the fact that hydrogen atoms have spin, and you can see that it's going to spin one way or another depending on which way it's oriented. And what we're finding is that in a regular sample that's not under a magnetic field, the hydrogens can be shown to be pointing in any direction. So you might like to think of this one as being an up arrow, and this one here where it's going in the opposite direction as being a down arrow. But in a regular sample, all the hydrogens can point in any way they like. However, when we apply a very strong magnetic field to these hydrogens, they will align either with or against the magnetic field. And you can see that these are all now not just pointing every which way, but aligned for or against the magnetic field. Further, we can get these to flip if we apply the correct radio frequency to the particular hydrogen that we're talking about. So this is what a proton NMR spectrometer looks like in schematic form. You've got a very strong magnetic field on this side. That's this thing here. That's the big that's a big magnetic field that we're applying. Around the sample, which is typically in a very long glass tube, we have a radio frequency transmitter, and this is for transmitting the various different radio frequencies that we're going to need to flip these different hydrogen atoms. So it turns out that the frequency at which hydrogens flip depends upon their environment. It depends on the different things that they happen to be attached to. And you can see various different kinds of hydrogens here in this spectrum. And we've got the ppm scale on the bottom, which is what we typically use to measure frequency in proton NMR spectroscopy. It goes from 0 to 10. And we have two directions that we talk about. This is upfield towards the right and downfield towards the left. Now it turns out that hydrogens in an environment where they're just connected to carbons tend to be upfield at around 1 ppm. And as we add electronegative atoms into the mix, you can see that the field increases, and we get, for example, a CH2 directly connected to an oxygen will be about 3.7 ppm. And then when we add double bonds and aromatic rings, the field strength increases even further to 6.4 and 7.34 ppm. So these are the frequencies that are required to flip these various different kinds of hydrogen atoms. And this is the underlying principle of NMR.